how baryons affect dark matter distribution with inflows and outflows.
And sorry, this is the pointer that worked with this.
I think so.
Okay. Hello, so my name is Jonathan Freundlich, and I'm a postdoc at the Hebrew University working with Avishai Dekel. And so today I'm going to present a relatively simple toy model that aims at describing how baryons can affect the dark matter distribution, and both the dark matter distribution and potentially also the formation of ultra-diffuse galaxies. So this is work in progress together with Avishai, with Fangzhu, who is going to present something very much related to this work today afternoon, Sharon Lapiner, who is also here. And to start with, I would just want to say a few things about the Q-score discrepancy. You probably all know that dark matter-only simulations predict relatively steep, cuspy dark matter profiles for dark matter halos, while observations infer relatively shallower cores. And this can notably be seen in this plot for dwarf galaxies, where you have the cuspy NFW profile here, and observations that seem more consistent with core at the center of the halo. So the thing is that, yes? So the thing is that when you add baryonic processes, and in particular feedback processes from stars and active galactic nuclei into hydrodynamical simulations, it is possible to reproduce chord profiles and thus to alleviate the discrepancy. But why would baryons affect and produce cores? So there are different ways through which baryons can affect the dark matter halos. There is, first of all, adiabatic contraction and dynamical friction, but probably most importantly, there are different potential fluctuations that can affect the dark matter profile from feedback processes. So you have cycles of inflows, outflows due to feedback that induce fluctuations in the mass profile, in the mass of the halo at different radii, and this means fluctuations in the potential that result in moving away the dark matter particles from the center of the halo, and hence contribute to forming a core. So in some sense, these potential fluctuations, or these mass fluctuations, dynamically heat the dark matter and hence pervade the distribution of the dark matter. What's happening? Okay. So a relatively similar process can be invoked as well to explain the formation of ultra-diffuse galaxies. So this is a class of galaxies that has been observed recently, owing to deep imaging of nearby clusters. And these galaxies are characterized by relatively low mass relative to the size, so named to their size. Namely, they have the masses of typical dwarf galaxies, while their sizes are more comparable to the Milky Way size, as can be seen in this picture. So there are different scenarios that can explain the formation of such galaxies. And one of these scenarios was developed by Ariana Di Cintio and precisely invoke the possibility that feedback processes, and more precisely cycles of inflows and outflows, result in not only puffing up the dark matter distribution, but also the stellar collisionless distribution. And in both the work by Ponsen and Governato, from which the previous figures were taken, and from the Ariana Di Cintio paper, were mostly phenomenological articles that relied on hydrodynamical simulations. So here, we would like to have an a priori toy model that would explain from scratch what happens between the baryons and the dark matter particles or the dark matter halo, and try to describe as simply as possible what's happening. So to do that, we consider a spherical shell in a dark matter halo or in collisionless that encloses a certain amount of collisionless mass, so that can be either dark matter or stars, if we want to describe the formation of ultra-diffuse galaxies. And we want to predict what is the evolution of this dark matter shell when we put mass or remove mass from inside of it. So if the addition or removal of mass is sufficiently slow, we are in an adiabatic case, so akin to adiabatic contraction, and the conservation of the angular momentum and circular orbits yields a certain ratio between the final radius at which the shell will be divided by the initial radius. But the case that is going to occupy us here is when this mass removal or mass addition occurs sufficiently rapidly to be considered instantaneously. And then it's a non-reversible process which we're trying to model. So the idea is that in the initial setup, we have an equilibrium, a halo at the shell is in equilibrium with its total energy given by its potential energy plus the kinetic energy, where the kinetic energy can be set by the Jeans equation, which describes the equilibrium of the halo. We assume that when we add or remove mass instantaneously, the gravitational potential adjusts itself instantaneously as well, but that the velocities are frozen such that there is a sort of transitory state where the potential is the sum of the previous potential plus the additional term due to the addition or removal of mass, and the kinetic energy is still the same as before. So this is shown here. In blue, you have the potential that goes, that instantaneously adjusts while the kinetic energy remains the same. And in a third stage, the system relaxes to a new equilibrium where the potential energy is here and the kinetic energy is again set by the equilibrium of the halo. And this is something that is in this stage. And what we assume here, the main assumption is that there is energy conservation between this stage and this stage, in the sense that shells enclosing a given collisionless mass conserve energy such that when we sum the contribution of the different energies, we have a constant here. So in Dutton et al. 2016 considered the case of an isolated shell, in the sense that they assume that the kinetic energy was given by the virial expression of the kinetic energy, which is usually more relevant for a halo, and they neglected the contribution of the outer shells to the potential, writing U equals minus Gm over R. So from this, they obtain an expression for the ratio between the radii. They also considered the case when you have an adiabatic inflow followed by an instant outflow, and this is the expression when combining both episodes. Finally, they also considered a succession of many such episodes. And the thing is that as through the Bastub model, there is a relation between the mass loading factor and the integrated efficiency of star formation, epsilon SF, which is proportional to the stellar mass, it is possible to relate this ratio to epsilon SF, and this is what they did to compare the results of the simulations with the results of the analytical model. So it's not very clear, but you can see in this plot a comparison between stacks of the Niehaus simulations from the Dutton et al. Paper with the prediction of this relatively simple toy model, and you can see that the behavior in terms of epsilon SF, which is the color here, is well reproduced. So in this article, they notably showed that the behavior of the halo would depend on the stellar mass or on the integrated star formation efficiency, with low mass halos being expanded while high mass halos would contract. And the thing is that in this work, there are two major assumptions that are not fully justified in the sense that, first of all, it neglects the outer layers of the halo. So if we try to express the total potential energy of a shell within a halo, there is a contribution, an additional contribution of the outer shell, which makes the potential not equal to minus Gm over R. And this is notably shown here. This is just analytics for an NFW profile, where you have the real potential here, the plane lines, and the dashed line correspond to minus Gm over R. So there is an additional term. And the second assumption that was made was that the kinetic energy of a shell inside a halo was given by the virial expression of the kinetic energy. And this is shown here for one example of a Nihau simulation, where you can see the real kinetic energy compared to the expression derived from the virial expression. So here, we would like to express, to do a toy model that would describe the evolution of the density profile of a halo. And for this, we need to express the different quantities for each and every shell and take into account the global distribution of mass inside the halo. And so to do that, we use the parametrization of the density profile that was described by Deckel and Tal in 2017, and which expressed the mean density of the halo in this form. And this is a form that was tested on the Nihau simulations, and it gives fit as good as NFW fit, both for dark matter only simulations and hydro simulations. It enables to have a varying inner slope of the profile, and this is important if you want to describe the evolution from cusp to core. And last but not least, it also has an analytical potential, which is what we need for our model to be analytical. So from this profile, we can derive what should be the kinetic energy, assuming first complete spherical symmetry and an anisotropy parameter that is equals to 0, so which leads that the kinetic energy in the shell is 1.5 times the radial velocity dispersion to the square. And then we use the Jeans equation to derive the expression of sigma r squared. So there is both the contribution of the collisionless particles and of the added mass that we add at different radii on the halo. So this term depends, of course, on how we add mass. And here in the following, we will assume that at each radius, we add or remove mass, and we do the calculations as if this mass was added at the center or removed at the center, which maximizes this term at each radius and gives the proper order of magnitude. So this is the summary, in some sense, of the model. So basically, these are the 3 steps that are already mentioned. If we have a parametrization for the potential energy and for the kinetic energy as follow, we can derive the initial parameters Pi from the initial conditions, so given, for example, by the simulations. And then we can obtain the final parameters Pf by minimizing the difference between the energy in these states and in these states. And we have also the radius of each shell where it is, but this is directly given from Pf by the fact that we assume that there is mass conservation between the shells, and we're considering shells enclosing the same mass. And from this, we can derive the behavior of the whole density profile, as can be shown here. This is the initial profile, and this is the final profile this is an analytical situation. And so finally, we want to test this model on real simulations. And this is what we do here with the Nihau simulations, which is a set of about 100 cosmological zoom-in simulations with and without baryons, and which has a resolution of about 1% of the virial radius. And this is what it gives. So this is the result. I will zoom in, don't worry. But it was just to show that, so here I'm trying to check for one simulation, one galaxy, all the snapshots, and see if the model is able to reproduce or predict the evolution of the density profile or not. So the white and yellow snapshots correspond to snapshots where we don't expect much things to happen because the infall or outfall or outflow is relatively small, while the green and red snapshots corresponds to cases where there is significant inflow or outflow. And so the green corresponds to a success, the red to a failure, and here yellow is a failure and white is a success. So the most important cases are those where there is indeed something that we expect to happen, so there is inflow and outflow. And as you can see from the general color overview, there is a success rate of about 80% with this implementation of the kinetic energy. And if we zoom in here to two successful cases from the previous plots, you can see more what's happening in the sense that here in gray, it is the initial density profile. In black, the final profile, and the red dashed line correspond to the prediction of the model when we consider the mass that has been put in or put out of the system. And this is a case where mass is being added onto the system, and thus there is, this can be seen here. So blue corresponds to inflows, while red corresponds to outflow, and thus the profile steepens accordingly to the results, outcome of the simulations, while in this case, mass has been removed, and there is a fair agreement between the two. So, yeah. So this is to show the kinetic energy, so in the sense that the black line is the real kinetic energy from the simulation, the red line is the one that is modeled here, and the green is what would have been modeled assuming the virial expression of the kinetic energy. So as you can see, there is still a discrepancy between the two, which might be due to the fact that here we're considering spherical system, while there might be non-sphericity. And the results, it is possible that the reason why this is still fine is that the non-spherical part of the system might not be as sensitive to the inflows and outflows as the spherical part. And so this is where I finished. So basically, I presented a relatively simple theoretical model based on inflows and outflows that can explain the formation of cores in dark matter halos or the formation of ultra-diffuse galaxies by puffing up the collisionless distribution. And the preliminary numerical tests seem in agreement with the model predictions, actually with very good success rate. And so there are, of course, things that still need to be thought of. First of all, the fact that we need to test the model a little bit more systematically, maybe with different time steps, or also to test if we can predict the evolution from a series of different events. We should check if we can explain why the model fails when it fails, if it's something related to the shape, to presence of a merger, or something like this. There is still this open question of the kinetic energy. And the last 2 points that I would like to finish with is first, the fact that there have been other descriptions of the core formation. And in fact, I worked on another description. And I think it would be very interesting that to compare with different approaches. So these two approaches here describe the whole process in a more diffusive way, while here we're talking about inflows and outflows on a global scales. And finally, I didn't talk that much about ultra-diffuse galaxies here. And one of the questions is whether this is the only mechanism that can explain the formation of UDGs. And this is something that Fangzhu will be talking about today. So I'm leaving it to him. Thank you.
Great, we've got time for a few questions. Turn the lights on. Okay, is that wake people up?
Okay, so basically here when I'm talking about, so for example, in this plot, this is just the prediction, the analytical prediction from the minimization of the energy difference. So here we don't talk about timescales, but of course when we compare to simulations, there will be some relevant timescales. And this is still something that we need to explore in the sense that I would expect that there is a specific timescale that is most relevant for this transformation, which is related to, for example, the dynamical scale in the halo. And yes. So far, this was just compared at the scale of so this is 200 megayear, the time scale between two snapshots. And the dynamical, I think it's close to the dynamical time scale, but I have to check. Yes. Yeah. Yeah.
Other questions? Say a word or two more about the kinetic energy problem, the problem with kinetic energy. I
Yes.
sort of missed exactly the nature.
Okay, so one of the issue is basically to try to have a proper analytical prescription for the kinetic energy. And so here we derive it both from complete spherical symmetry. So that's relatively simple. And if we check the different terms that are being assumed in this stage in the simulations, this assumption seems to be relatively valid. And then we also assume the Jeans equations. So here in this form, we assume again that beta equals 0. But the thing is that the Jeans equation in the simulations may not be valid at all radii. And in particular, near the center, the Jeans equation seems to be not valid, so which might create some discrepancy and might induce us to only take into account the model after a certain radius, not to take the very center, because here the Jeans equation is not a very good assumption.
Great. Well, it's now time for us to have a coffee break, so let's thank Jonathan again.
Just a very quick announcement. A ring with some gems on it was found in the women's restroom this morning. If that's yours, see Brendan Wells just outside.